moving to ESD106. Next lecture onwards, it will be held automatically in ESD106. Incidentally, we are swapping with Professor Venkatesh Ramaya, who is also offering property foundation for electrical engineers for MTech. Okay, incidentally, if you come and then sit, the same topics will be covered, but that is for the end. But you have to attend my quiz to get my that is only his class strength is 65 or so. Ours is close to 90. That's why we are swapping. So we are almost through with the expectation of discrete random variables. Then we will move on to moments and central moments in general, and in particular on variance of discrete random variables. Then we will touch upon a little bit about the joint mass function of two or more random variables, marginal mass functions, conditional probability mass functions, and so on. So before we move on to continuous valued random variables. So with regard to the expectation, E of x or a discrete valued random variable is defined as probability that x element of Sx, where Sx is the range of values the random variable x can take. X is the particular value of x into probability that x equals to x. This is the general definition of expectation the random variable. We looked at the expectation of the Bernoulli random variable and also the binomial random variable. We will quickly look at the other expectations. So if x is geometric random variable with the probability p, what it means? That is the number of trials to get the first success. I am not sure whether it derived to get the first success. I think this has been derived maybe. Okay. So that p equal to expectation of x is equal to 1 over p, that p is the probability of success. Okay. So this is for the geometrical value. Now we will make use of this. Then let's take x, which is negative binomial. That is the number of trials we have to conduct to get certain number of successes. Let us say R successes. So number of trials to get R successes. So what is the corresponding probability mass function? To put it in this part. So let's say we have to conduct n trials, then r minus 1 successes should occur in k minus 1 trials, and then the remaining one has to be a success. So this is what is the general formula. So k minus 1 r minus 1 into p power r minus 1 into q or 1 minus p power n minus 1 minus r minus 1 into p. So that will be k minus 1 r minus 1 p power r plus p power n minus 1. So this is the formula. So what we have to do, we have to put it here. We have to get the expectation of x is equal to. So in this manner you can do the range of values k can take is r onwards, because to get r successes we have to conduct a minimum of r times. So it is k is equal to r to infinity k into this. And then you can do all these things. Okay. But let's make things simple. We have already seen that the linearity of expectation we will make use of it. what can happen is, okay, this can be one particular sequence, particular realization. So you may get failure, failure, success, failure, success. Something like that. Suppose let us say you are looking for 4 successes. Then this is when you will stop. 1, 2, 3, 4. So you will count the number of times in this particular realization. You will count the number of trials, and that is what we call the value of the negative binomial random variables. So how can we view it? Each one of the Bernoulli trials is an independent. They are all IID random variables. So if you look for the first success, that is nothing but a geometric random. The number of trials to get the first success. So here in this case, this is 3. So we have a geometric random variable because they are taking a real value of it. Then you look for the second success. That is going to be another geometric random. The total number of trials to get the second success is the sum of these 2 random geometric random variables. Because the value taken by this geometric random variable will not influence the value of the next geometric random variable. Each trials are independent. Therefore, if you split them into geometric random variables, they are also independent. So I can call this geometric random variable as G1, this as G2, this is G4. So we can write this X as a summation of geometric random. We are looking for R successes. So we use just R geometric random. They are all independent. But the independence is not required, of course, for our case. So now we are asking for the expectation of the negative binomial random. By linearity of expectation, it is expectation of G1 as expectation of G2. And we know that each one of these geometric random variables expectation is 1 by R. It's not 1 by R, 1 by B, 1 by B. So together this is R by B. So this way we can easily get. Then we have the discrete uniform. So it can take value integral values between 2 limits a and b inclusive of both a and b. That is the general thing of the, and all values are equiproper. That is the discrete uniform random. So what we will do is without loss of generality, we will take the values taken by this random variable. Okay, they are in the range 1 to n. We are taking a to be 1 and then b to be n. So if you look at the probability mass function, so it's all like this, and this value is equal to 1 by n. So x is like this one, discrete uniform between 1 and n. Usually we put U for uniform. I am just putting D because it is discrete uniform, not a continuous uniform. So what is the expectation of x? It is just that the probability is 1 by n, and then I will put sigma I is equal to 1 to n x px px equal to x. This is the general formula. The probability that we take any value is fixed one, that is 1 over 2. And this is what, sorry, this is I. So this is 1 over n, which I can take it outside. and this is nothing but summation of n plus 1. So this is the expectation. Yeah, we come to variance in a little bit later. Then we have the Poisson. Random variable. So x is Poisson. The parameter is defined as lambda. So expectation. So again PM of x. Probability that x equal to k. What is it? Can take only non-negative integral values. So this is the PMF of the Poisson random variable. So expectation of x is sigma k is equal to 0 k times, because k is in x. Okay, k times probability x equal to k. And 3 power minus lambda, lambda power k by k factor. So what I can do is sigma k is equal to, because k is 0, I can put so we will take one lambda as well as 3 power minus lambda outside. K and one thing you will k and k factorial becomes k minus 1 factorial, and because we have pulled out the lambda, we get lambda power k minus 1. So lambda e power minus lambda. So I will change the variable. I is equal to k minus 1. So for Poisson random variable, the parameter lambda is the expectation. That is how we have to interpret. Well, now we have looked at the expectation. This is one of the statistical averages. In general, all these are statistical averages, which will give you some rough idea about the behavior of the random variable. Because a random variable, to specify it, you have to give the CDF or the PDF or the PMF, which are the characteristic functions. All these are, if you give one, other can be found. So, but it's a function. It's not easy to interpret it. But if you want some numbers with which you can get some meaning out of it, these are those statistical averages. Expectation is one of the important. There are also other things. One is the mod, another is the median. Then we will see variance, standard deviation, and in general moments and so on. So mod is the one, is that value which is most probably most frequently occurring in the list of reality. If you make a number of trials of the random experiment and note down the value of the random variable, that value which gets repeated quite often is likely to get repeated quite often is what we call as the mod. So if I do it 1000 times and then find the fraction of the time that value the random variable takes, that gives me the probability of the random variable, which means that x mod is the one which is most probable to occur. So if x is the random variable and x mod is a particular value such that probability that x equals to x mod is greater than or equal to probability that x equals to x for all x not equal to x. So this value is more. There is no other value which is has more probability than this. That is one. And again, it need not be unique. There can be two values which can have the same probability. Then it is multimodal. Then median. See, this will not tell you that you can expect this. That is totally different. Okay. It will tell there are some values which more likely to occur. For example, a random variable can take values 1, 2, 3, 4, 5, and 5 may be most likely to occur. But that will not be the expectation. Expectation is not also average of 1 over 5. It is weighted by the probability and then you take the average. The value that you would expect. Okay, it is not the average over just value. It is weighted by the probability. Then median is such that if you take a very large number of realizations, okay, it is that value such that the probability that the random variable will take value less than that value is equal to the probability it will take more than. In some sense, it is center. Okay, probability it will be less than that particular value is equal to probability that it will be more than. I will call it as x mean. This is also one more thing. Then, so we have a random variable whose expectation we found out. But we want to know more about this one, about the behavior of the random variable, how random it is. That is what we want to quantify. Sometimes the expectation will give you some, okay, will make the values of random variable which will not show how the random behavior of them. So sometimes we may not be interested in the actual values, how dispersed they are, how randomly they behave is what we may be interested in. So what we would like to do is that if x is the random variable, it may say, for example, a random variable can take values around 0. May take values -1, -2, plus 1, plus 2, sometimes -3, sometimes +4, but these are the values in between. So it's all around zeros in some things. Sometimes we may have values which is 1000, 998, something like that, but it may also take. It may also be behaving like this. But only thing is, if you take the expected value, it will be around 1000. So this large number is distracting us. What we are interested in is how is it dispersed about certain value. So to get away with that large number, so only we are focusing on how much it differs from some central value, from the expected value. If you want, that is what we want to focus. We can subtract the expectation from x and define another random. So we will define a random variable y, which is x minus e of x. So that 1000 will be removed from this. I will subtract 1000 from all of them and look at that random variable. That random variable will have around 0, +1, -1, 2 and something like that. So if you look at this random variable, the behavior of this, how this random variable y will be. One thing we can easily say is, if you look at expectation of y, what is it? It's the expectation of x minus e of x. again you can apply this formula, that is sigma x element of s x minus g of x of dx equal to x. So that is again and so on. So this is nothing but g of x. Because what? This is the definition of g of x. And what is here? G of x is a constant. It can be pulled out. If you pull this out, the remaining thing will give you what value? 1. Because it is sum over the probability. So this is nothing but minus 2. Okay. So which means that what you get is 0. So this random variable is opaque, which has mean 0. Sometimes we will use the word term mean to denote for expectation. Expectation is a more formal word, but mean can also be used. But let's not use average and so on. So this random variable y property, if you are analyzing, that will give you better meaning about the original random variable x. Then we also looked at if x is a random variable, and if there is a real valued function g of x, then we can define another random variable y, which is g of the random variable x. Then we also saw that e of y can be found out by first finding the probability of y, of PMF of y, and then taking the average. That is or alternatively using the law of unconscious statistician. Then interchangeably use this material so that you are comfortable. So this also can be done. So this is the expectation of g of x. So the expectation of a function of a random variable can be taken by simply summing the value of the function at different values of x weighted by the corresponding probability. We know this one. Now, for some specific value of g of x, we will try to find the expectation. Some functions which are of interest to us are of the form x power 2. The reason is, of course, once we know about this one, any polynomial can be written as terms like this. So, if that is the case, then the expectation of x power n is this one. We will call this as the moment. And this, because it is m, it is called as the mth moment. And it will be useful to understand the behavior of the random variable. Of course, we know the first moment is nothing but e of x, which we have already discussed well. One more moment which very frequently we will use is the second moment. E of x. So moments can be defined. Then we also looked at, we can subtract the expectation from a random variable and define functions like y, okay, which give you which will remove certain unpleasant large values or small values of x and give you the dispersion around certain 0. And we can also think of the moments of y. That is, we can also define y equal to x minus e of x and then define the expectation of y power x. So what is that? That is expectation of x minus e of x this is nothing but remove the mean from it, take the power m and take the expectation. So we can this will also be useful. Henceforth what we will do is this writing this e of x is slightly maybe cumbersome or something. We will use a shorter notation for this expectation. We will call it as, we will use the term mu x. So when we say henceforth mu x, we mean the expectation. So what is this? The other way of writing is x minus mu x power m expectation is the mth moment of y, or in terms of x we will call them as central moment. Why central? Because from x we have removed e of x and then we take the moment. So these are called as the central moment. There are also something called components. I will not get into it. You will encounter it someplace. You will not look into it at this stage. You will later, because time permits, you will get into it. That is also another kind of moment that will be of importance. So central. Now we will spend some time on central moments. And in particular, although there are many central moments, we will only discuss about few of them. First is, what is the first central moment? What does mu mean? That is x minus mu x. Henceforth, this is the one we are going to talk about, and we are going to take the expectation of this first power of this. So what is this? This is e of x. I can apply this one minus mu x. First, so the first central moment is always then the second central moment. Again by definition, x minus mu x will whole squared expectation of that, and that is very important. Why? Because you have removed the mean value and then the values now will be around the mean. What is this? This is the deviation from mean. And that can be positive or negative. And in fact it has to be positive or negative because we are subtracting from mean. For the mean to be 0, okay, for mean need not be 0. This need not be positive or negative. Okay. Only from the central y it will be positive or negative. So it is the deviation from mean. Yeah, it has to be positive or negative. Sometimes it has to be more, sometimes it has to be less. Then only mu x will happen to be. Now that quantity, if you simply take an expectation, we will get 0. That is what it shows. You can simply take the expectation of x minus mu x, because if you take positive and negative values, okay, equally likely also you get that it is 0. But we want to know the dispersion around the mean. To remove that, both sides of values being taken around the mean, there are two ways in which you can do. You can take a mod or you can square it. Now if you square it, we are getting deviation squared, and which will always be positive. And if you take the expectation, this will give you the magnitude of dispersion from the expectation. That is gives the spread of the values taken by the random. So it tells the variation of the values taken by the random variable around the mean. So it is called as the variance. And in short, we will write it as VR of x. Then here we have taken a square. So it is if you look at the unit, it will be double of the value of the random. So to bring it back, the square is basically taken to avoid this positive, negative, and so on. So if you want to again get a value which is on par with the values taken by x, you can take a square root of variance, and that is usually denoted as sigma x, and it is called as the standard. So these are something which is very useful or basic statistical averages that tell you about the random behavior of the random variable. So we will, for different commonly occurring discrete random variable, we will find out these things and then try to look at the behavior. One more thing that will be useful is the coefficient of it. We will use the notation Cx. That is nothing but sigma x by p of x. So this is again one more quantity that will be of use. Before we start looking at the variance of the expectation we have already done, variance of different discrete random variables. Let's look at some of the properties of the expectation as well as the variance, generic properties, which will help us to derive the variance easily. The first thing about the expectation. So x is a random variable. E of x is the expectation. We have looked at how for a g of x we can find the expectation. Okay. We will take a very simple case of the g of x, which is just a linear function of x. A times x plus x, where a, b are constants. So in this case, E of g of x is E of a times x plus b. You can actually apply this formula and so on. This is the way we have done it there. It will turn out to be a times E of x plus b. Why? Because if you take, you can individually take x from x. You can a times x. A can be pulled out. You will be multiplying x, p of of x and then sum it over. You can pull out a. The remaining thing is e of x. A times e of x. And b and the remaining summation. B can be pulled out of that summation. That is nothing but the sum over the property, which is 1. So you will get this one. It will also tell you that if you want to take an expectation over a constant b, you just b itself. B is a random variable which is a constant. So this is something we know, we can also generally a1 x1 plus a2 x2 am xm is equal to a1 e of x1 plus am e of xm and so on. So these are some properties of the expectation. Yeah, everything follows from the linearity. Then about variance. The first thing that we will try to do is that is, by definition, this x minus mu x reverse. Okay. Then we will try to get an alternate way of writing it, which will be more easy for us to compute the variance. So if you square it, you will get x squared minus plus mu x whole square minus 2x mu x. Now we take the expectation. Whenever we take the expectation, remember what we are doing is sigma x element of Sx, that whatever we are taking times, I will put it as dot times p of x equal to this. This is what we are doing. This operation amounts to this. On the dot is the placeholder, here it will be x squared, here will be this one. This is what we have to do. So, if you do this one, here what you have, it will be x squared times this one, which is the second mode. I will write it as x squared plus, if I take it on this one, mu x is a constant. Having found the average or expectation, that becomes a constant for a random variable. Square is a constant. So expectation of any value is the same value. So it is just mu x squared. And if you take the expectation over here, x is a random variable, whereas 2 as well as mu x are constants. So they will come out leading to 2 times mu x into e of x. It is again nothing but 2 mu x the whole square plus mu x square. So you get cancelled. You have e of x square minus, only one of them, one minus will be remaining. Instead of writing mu of x now, I will revert back to the original convention. E squared of x, or e of x equals to be, if you want, we are just confusing. This is what we do. So now we have a more easier or a working definition for finding the variance of x. It is e of x squared minus e of x equals to. So this is something you should remember it very well, because this is what eventually we will all be using for finding the variance. Variable for which we know the variance. Variance of x is being found out. We have to deal with. Now we have to deal with a function of x. Okay. In particular, we will start with simple function. One function g of x, which is nothing but a scaled version of x, a times x. Then what will be the variance of g? Should we again find out the characterization of g of x and then do all these things again? Or can we write it in terms of variance of x? Then it becomes easier. So that is what we will try to do. So again, what is this variance of a times x? is expectation of, in place of, this is the, now we have to find, we have to put it in the basic formula of variance, which is A. So A times x, and you should subtract the expected value of A, which is A times mu x, square it, and then take the expectation. So you will have the expectation of A square into x minus mu x the whole square. That gives you A square can be pulled out. And that is nothing but so if you multiply it by A times x, the variance becomes A square times variance. We can even generalize it. So now g of x is ax plus b. Okay. Then what we have to do is here ax plus b minus a mu x plus b the whole square expectation. First thing you notice is this b gets cancelled, and the remaining thing is very similar to the other one. Okay, which will again lead to a square times variance. Simple reason becomes, or you take the variance. Okay, we will talk about the how variance can be applied. Here it can be applied individually. Variance of b is 0. So this is very important. Variance of b, where b is a constant, always 0. Variance gives the dispersion. In lot of realization, how the values taken by the random variable get dispersed. But this is a constant or random variable. It's always takes the constant value. It doesn't vary at all. So the variance is 0. So this is how we can. Then one more thing. X plus y will. X and y are two random variables. For expectation, this E of x plus E of y. That's the linearity. And x and y mean not, I don't even tell anything about x and y. The concept of independence we will discuss it. We are not even invoking any of those things. So always E of x plus y is E of x plus y. How about the variance of x plus y? Again, we will go back to our first principle. We will apply the formula. So x plus y minus of E of x plus y, and then square it and then take it. So we will conveniently rearrange the terms. X minus E of x, which is mu x. I will put it as x minus mu x. Okay. Plus of y minus mu y, the whole square term. Clear? Then you square it, and then after squaring you will get three terms: square of this, and the cross term. And then you have to take expectation. But now we can use linear difference. You will get E of x minus mu x the whole square expectation plus expectation of y minus mu y the whole square expectation minus 2 times expectation of x minus mu x into y minus mu y, like this. there, I would have been happy, because see, variance of x plus y is equal to variance of x plus variance. I can, this is nothing but variance of x plus variance. The linearity of expectation follows for the variance. But this term spoils this easier way of dealing with it. So we have this term. Okay, we will give a name for this. If x alone is there, what we do? We take the central value of it, x minus 2x, and then square it and call it as the variance of x. Now there is one x minus mu x is there. Similarly, y minus mu a is there. Instead of squaring, this is also a power. The two things are there. But one is x, one is y. So we will call it as covariance. So we will call this function as covariance of two random variables which are x and y. We will use the shorter notation as COV of x comma y. So we have, for the case of two random variables, we have a formula: variance of x plus y is equal to variance of x plus variance of y minus 2 times covariance of x comma y. For that needs to be found out. Suppose we have a case where the covariance is 0, then we can say that variance of sum is equal to sum of variance. So note this one. We will meet in case 106. So if you have two random variables x and y, for which if x and y is such that covariance of x comma y is equal to 0, then we will tell that x and y are uncoordinated. We will say that the random variable x and y are uncorrelated. If this happens to be 0, then the variance takes an easier form. We will later define a notion of two random variables to be dependent or independent. Jumping ahead, because this is very close to them. If two random variables are independent, then they will be uncorrelated. Then this formula will hold. We will show that when we talk about independence. But it is to be noted that if two random variables are independent, they will be uncorrelated, and variance of sum is equal to sum of variance. It becomes easy. But if they are uncorrelated, they need not necessarily be independent. Just remember it. We will talk about it again. Now, why we do all these things to get this one? Because now whatever we are going to do now, that we will leverage this.
Over.
So,
Yes.
So we will